Think about the moment a golf club strikes a ball. It's a violent, instantaneous collision. If we wanted to measure the exact amount of force applied in that split-second impact, we run into a major physical problem. In a baseball hit, the actual contact happens in just fractions of a millisecond. That window is far too small for any standard instrument to measure the force directly as it changes. So instead of trying to capture the force in real time, physicists work backward. They look at the aftermath, specifically how the object's momentum changed as a result of the hit. To see how that works mathematically, we start with Newton's second law. This states that force equals the rate of change of momentum over time, written here as F equals dp over dt. By multiplying both sides by dt, we isolate the change in momentum. Then we take the integral of both sides across a specific time window. That mathematical step gives us our final state, p2 minus p1. That final change in momentum is what we call linear impulse. It is crucial to understand that impulse is not momentum itself. Rather, it is the exact measurement of how much an external force altered an object's state of motion over a specific window of time. That calculus derivation can look intimidating, but it provides the foundational logic that applies to any impact, regardless of complexity. For many everyday problems, we can rely on a simpler algebraic shortcut. Let's look at the most basic case. If the force applied to an object remains constant and doesn't change, we simply pull that force variable outside the integral. This leaves us with a clean formula. Impulse is simply that constant force multiplied by the total change in time, or delta t. This is a force versus time graph plotting that constant force, which creates a perfectly flat horizontal line. The time window forms the width below it, giving us a shaded rectangle. For constant forces, you drop the calculus entirely. You are literally just calculating the area of a basic rectangle. Base times height gives you exactly the same result, proving that complex physics equations often translate directly into basic geometry. This is an updated force-time graph, showing a more realistic scenario. Forces like a bat hitting a baseball aren't constant. They spike up dramatically and fall back down. But the logic holds. The integral from our first equation simply represents the total geometric area trapped underneath this curvy graph. Before you calculate that area, you have to account for directionality. Because force is a vector, the direction of the push or pull dictates whether you are adding momentum to the system or removing it. The strict rule for force-time graphs is straightforward. Any area above the time axis is positive, meaning it adds momentum. Any area below the time axis is negative, meaning it subtracts momentum. Let's test that logic. This force-time graph displays a positive triangular force and a negative square force. Pause the video here and calculate the total net linear impulse. Let's break it down. First, we find the area of the top triangle, which gives us a positive 10. Then we calculate the area of the bottom square, giving us a negative 4. Subtracting the negative area from the positive area leaves us with a final net impulse of positive 6 kilogram-meters per second. The net area on a force-time graph accounts for every fluctuation in push and pull, providing a complete record of the total momentum change. This brings us right back to our opening examples in sports. This is a force-time graph mapping a massive force applied in a microscopic fraction of a second. The curve shoots up into a needle-like spike. Even though the window of time is incredibly narrow, the peak force is so high that the total enclosed area is still massive. That large geometric area guarantees a massive shift in the object's momentum. Physicists have a specific term for this extreme pairing. A large force acting on a body for a very small amount of time is called an impulsive force. Let's pull everything together into a final framework. You might want to screenshot this upcoming screen. First, remember our fundamental definition. Linear impulse always equals the exact change in momentum. Next are our two calculation methods. If the force is constant, you use the algebraic shortcut, force times change in time. If the force is variable, you use the geometric method, total area under the force-time graph, subtracting any area below the axes. Whether calculated through calculus, algebra, or visual geometry, these methods all quantify the same physical reality, the specific way force transforms motion over a window of time.